This is your presenter Asloob Mudassar, and I am presenting slide number 99 of the course on laser physics. Question is, laser diodes as pump lasers are generally categorized as single strip, diode array, diode bars, and stacked bars in the order of increasing optical output power. Give a brief description of each of these with the support of schematic diagrams. The answer is the schematic diagram of a single stripped semiconductor laser is shown in figure 1. So here is figure 1. So the caption is cross-sectional view of a single strip index guided semiconductor diode laser. You can see that this black area is actually the region, is the active region. So this is the active region from which this is the active region, and along the length of this semiconductor material, the lasing action will take place and the light will come out from this end, for example. So the beam is coming out from here, and you see that there are metal contacts at the upper face and at the lower face. There is an oxide layer. This will be described in the description of this figure. This is p-doped aluminium gallium arsenide, and this is the n-doped aluminium gallium arsenide layers. So this is the p layer, this is the n layer, and in between them there is a gain region at which we have the active medium there, and the lasing action takes place in the gain region or in the active region, and the beam will come out from here. The horizontal dimension of this is 3 micron. So this black region through which which is an indication of the active medium and through which the beam is coming out has a dimension of 3 micron horizontally and 1 micron in the vertical direction. So let's read the relevant description. The width of the strip is shown as 3 micrometer extending over the diode length through which the current passes. Current outside the strip region is blocked by the insulating oxide layer. So you see that I have shown you the oxide layer which blocks the current. This is the oxide layer, you can see. This is the oxide layer. So this layer will actually block the current flowing outside this region. So the current outside the strip region is blocked by the insulating oxide layer. The beam just in front of the exit window has horizontal dimensions of 3 micrometer and vertical dimensions of 1 micrometer. That is D parallel to the horizontal axis. D parallel is equal to 3 micron, and D perpendicular, which is perpendicular to the to the horizontal side, D perpendicular is equal to 1 micron. That is the vertical dimension is 1 micron. That is the vertical dimension of the opening of the opening from which the laser light is coming is 1 micron, and the horizontal dimension of that opening is 3 micron. The beam takes elliptical shape as it travels away from the exit window. You see that it has a major axis, for example 3 micron, and a minor axis, for example 1 micron. So the beam will come out as an elliptical shape beam. At the beam exit point, the beam cross-sectional dimensions are very small, thus produce a spatially coherent beam. Since the opening through which the laser beam is coming out, for example, as shown in this black area, from which this is the cavity of the laser, end of the cavity of the laser from where the beam is coming, the dimensions of this is very small. So that's why we can say that the beam coming out from that one is a spatially coherent beam. That is, there is a exact phase relationship between different parts of the beam coming out from that region. The half divergence angle in the two perpendicular directions measured from the beam center to the point where the intensity drops to 1 over E square of its value at the beam center have typical values of theta parallel to 5 is of the order of 5 degree and theta perpendicular is of the order of 20 degree. So theta perpendicular is actually the this you see that you can see that this dimensions is longer. So if you measure the if you draw if you consider the center of this beam and if you measure this angle, which is the angle of the extreme point of the beam where the intensity is 1 over E square of the intensity at the center, you see that I have drawn this spot that corresponds to the 1 over E square intensity of the intensity at the center of the beam. So this longer spot has a theta which is called as theta perpendicular and its value is 20 degree, whereas this horizontal part from the center this horizontal part is just 5 degree, as we have shown over here. And we have considered 1 over E square points. Assuming that the intensity is at the center is, for example, is 1, then we consider 1 over E square points and draw the spot of the lasers and draw the laser spot, because beyond that one the intensity becomes insignificant. So the intensity remains significant up to the points that we are and the diameter of the beam is measured and the diameter of the beam spot is measured at the points provided by the 1 over E square. And theta parallel is 5 degree, theta perpendicular is 20 degree, as I have just explained. And these are the half divergence angles. The beam has Gaussian profile along these two directions with the corresponding spot sizes as given by W naught is of the order of d by 2. Since this W naught is actually the radius of the beam spots along the two directions. So if you want to measure if you want to take the beam spots along the vertical direction, then you will use D will be used as a D perpendicular divided by 2. And if you want to measure the beam spot along the horizontal direction, then you will take D parallel divided by 2. The theoretical value of the angles of divergence can be computed using the equation that theta is of the order of 2 lambda over pi d. So this will give you actually the angle of divergence of the beam, where lambda is the lasing wavelength, which for a typical single strip diode laser is 800 nanometer for the geometry shown. So for the geometry that we have discussed in the figure number 1, that will emit a that is a single strip diode laser, and that is going to emit 800 nanometer for the geometry shown. Due to larger divergence angle along one of the beam axis, that is theta perpendicular is greater than theta parallel, because 20 degree theta perpendicular is 20 degree, theta parallel is equal to 5 degree. So theta perpendicular is greater than theta parallel. The beam major axis is rotated by 90 degree, just traveling a few micrometers from the exit window. So you will notice a point over here that the beam major axis is rotated by 90 degree. For example, if you look at this diagram, over here, for example, in this diagram, the major axis is along the horizontal direction. So along this direction, we have the major axis, and along this direction, we have the vertical direction, we have the minor axis. So the beam will come out, but due to diffraction, what will happen? Along the narrow opening, the beam spot becomes enlarged, and along the larger opening, the beam spot becomes smaller because of the diffraction, because the diffraction is more prominent along the vertical due to the vertical opening, which is smaller. So the major so the here so at the exit point, the major axis is converted into the minor axis, and the minor axis, which is along the vertical direction over here, is converted into the major axis. That is the major axis is rotated by 90 degree. So this is what I have mentioned over here. That is, since theta perpendicular is greater than theta parallel, the beam major axis is rotated by 90 degree just after traveling a few micrometer from the exit window. The optical output power from a single strip semiconductor laser generally lies below 100 milliwatt. So you see that you can determine the limit of the upper power, that we cannot obtain a power greater than 100 milliwatt from such a single strip semiconductor laser. A monolithic array of single strips can be fabricated on a single semiconductor substrate, resulting in the formation of diode array as shown in figure 2. So let's see figure number 2 over here. The caption is cross-sectional view of the monolithic array of many single strips on a single semiconductor chip. So this is the magnified view, and you can see that I have shown only one such single strip, single strip has been shown in figure number 1. And now you see that here we have combined a large number of such single strip semiconductor chips have been combined to formulate a larger strips, which we say that it contains an array of many single strips. So this is an array of many single strips diodes. A monolithic array of single strips can be fabricated on a single semiconductor substrate, resulting in the formation of diode array, which is shown in figure number 2. So you see that I have shown you a diode array, which is actually a combination of many single strip semiconductor diodes. Each single strip has a width of 5 micron, and center to center separation is roughly 10 micrometer. Diode array normally contains 20 single strips. The beam dimensions just in front of the exit window are 200 micrometer by 1 micrometer. That is, D parallel is equal to 200 micrometer and D perpendicular is equal to 1 micrometer. This is just in front of the exit window. The beam divergence is the same as that of a single strip. That is, theta parallel is equal to 5 degree and theta perpendicular is equal to 20 degree. The beams from the different single strips are generally uncorrelated, because there is no correlation between the phases of the light coming out from each of these single strip diode lasers. Under certain conditions, phase correlation may exist and the beam is converted into two lobes. So you see that this is a very special case, that a phase correlation may exist between some of the semiconductor single strip diodes. And you see that under such a condition, due to the phase correlation, because some of them have one value of a phase and the others have the different value of a phase, so we can have two lobes in that case. The optical output power from such a single diode array is around 2 watt. That is 2000 milliwatt. So you see that this is the upper limit from such a diode array. So this is what we have discussed, the diode array. You see that when we have discussed the single array, single strip diode, a single strip semiconductor diode array, the upper limit of the power was roughly 100 milliwatt. And since here we are combining nearly 20 such, and then we have 2000 milliwatt, or roughly 2 watt. So from this geometry, which is an array of diodes, you can an array of diodes of 20 single strip semiconductor chips joined together, we can obtain a power of up to 2 watt. Diode arrays can be combined. You see that I have given single strip semiconductor laser, and in figure number 2 I have described diode arrays. Now you see that now we are going further step ahead and we are talking about a diode bar. So diode arrays can be combined and fabricated serially on a single substrate, resulting in the formation of a monolithic diode bar, which is shown in figure 3. So let's have a look at figure number 3. This is. So you see that this is very long and you can treat it as a bar, diode bar. So the caption is a serial extension of a monolithic array of many single strips on a single semiconductor chip, resulting in monolithic bar. And of course, this is the magnified view of the chip. So let's read the descriptions relevant to this figure. Diode arrays can be combined and fabricated serially on a single substrate, resulting in the formation of a monolithic diode bar, which is shown in figure number 3. Typically, 20 diode arrays are combined to form a diode bar of length roughly 1 centimeter. Each array in the bar is roughly 100 micrometer in length, and the center to center separation between two consecutive arrays is 500 micrometer. There are 10 diode arrays in a diode bar of 100 micrometer length. So you see that here we are typically discussing that there are 10 diode arrays in a diode bar of 100 micrometer length. The emitters in the bar have component beams which are phase uncorrelated. The output power with these emitters may range from 10 to 20 watt. So you see that in the diode array we discussed that the maximum power that we can take from the diode array described in figure number 2 is 2 watt, because that consisted of 20 single strip semiconductor diodes on a chip. And now we have, for example, if we have 10 to 20 diode arrays combined together to form a diode bar, then of course the diode bar can have the power from 10 to 20 watt depending upon the number. So if we are using 20 diode arrays, then we have a power roughly of the order of 20 watt. And if we are using 10 diode array, then of course the power will be of the order of 10 watt. So from 10 to 20 diode arrays, the diode bar will give you a power range from 10 to 20 watt. So this was, you see that the diode bar which I have just described. And then the next step that we are going to describe is the stacked bar. Diode bars can be stacked on top of each other and can be fabricated on a single substrate, resulting in the formation of a monolithic stacked bars, which is shown in figure number 4. So let's have a look at figure number 4. This one. This is the stacked bar, We have the bars horizontally placed. These are the bars, and we have stacked them vertically. So this is called the stacked bars. So each bar is extending horizontally. So there are, for example, in this picture we have shown only 6 such bars stacked together on top of each other, and the figure caption is extension of monolithic bars. The monolithic bars are along the horizontal directions, and we have combined and we have stacked 6 of such bars. So extension of a monolithic bars on a single semiconductor chip, resulting in stacked bars. So this is again a magnified view. So you see that this is the picture of the stacked bars. The relevant description of the figure is, if 6 bars each of 1 centimeter in length are stacked, the light emitting area will have dimensions of 2 millimeter by 1 centimeter. The average optical power obtainable from such a device will be around 100 watt per centimeter square. For high power pumping applications, stacked bar diode lasers is used. Consider an example of Nd:YAG material which has narrow absorption lines in its absorption spectrum. The absorption peak occurs at 808 nanometer and has a bandwidth of 2 nanometer. So this is, you see that I am talking about the absorption lines. One of the absorption lines in the Nd:YAG laser, which has a peak absorption power at 808 nanometer, and the bandwidth of that absorption line is 2 nanometer. So if we want to pump such an Nd:YAG laser, we what should we do? The spectral bandwidth at this wavelength from a single strip laser is around 1 nanometer, which is quite favorable but has a limited power. You see that the bandwidth obtained from the single strip laser matches directly of the which is of the order of 1 nanometer, matches very accurately with the Nd:YAG laser, with the absorption line of the Nd:YAG laser just mentioned. But you see that a single strip will have a limited power. The bandwidth from stacked bars based on the same single strips could be larger than 2 nanometer due to temperature gradients and structural variations between the individual strips. To stabilize the output parameters of stacked bars, the device is cooled either by thermoelectric cooler or by liquid cooling. The temperature stability across the stacked bar is highly recommended and should not exceed a fraction of 1 degree Celsius. So you see that we can use a stacked bars in order to pump the Nd:YAG lasers. But of course, the bandwidth of this stacked bars is actually greater than 2 nanometer. So it means that some of the power will be lost because that is not going to match exactly with the bandwidth of the absorption line of the Nd:YAG laser. But of course, some power will be lost. But we can keep that one within our limits. That is, we can control the temperature of such a chip through either through thermoelectric cooler or by liquid cooling. And then if we can maintain the temperature, then of course we can maintain the bandwidth, and of course the power stability can also be assured. So you see that I have described. So I have described first the single strip laser, diode laser, and then the diode array, which was based on single strips, and then the diode bars, which were based on diode arrays, and then the stacked bars, which were based on diode bars. And I have given the description of each of them because the fundamental chip was provided by the single strip, and the joining of these one will give you diode arrays, and the joining of these diode arrays will give you diode bars, and the stacking of these diode bars will give you stacked bars. And of course the power from these to onward, that's from the single strip to diode array, and from the diode bars to the stacked bars, the power will increase drastically depending upon the number of elements that we have used in a single chip. And we have also given the relevant diagrams and tried to explain in the minimum possible way, and explained them with the dimensions, and also with the power range, and also with the wavelengths that we can obtain from such stacks. So this is the end of slide number 99.